www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
This is lecture 30 on heterojunction bipolar transistor. I'll have two lectures, and this is the first one. Now, this is some of the materials taken from Professor Mark Lundström's previous lecture on this topic. He has worked a lot on this particular problem for many years. So, it's sort of from both of us together. We'll start with an introduction that what is this heterojunction bipolar transistor? You probably have some idea already. And then again, new device, start with equilibrium solution. Draw the band diagram first. Don't worry about how it works. Band diagram number one. We'll talk today about types of heterojunction for equilibrium condition, the electronic transport problem, that how electron flows, what the gain is, and those types of things we'll talk about in the next class. But today you will see that there are much more variation in heterojunction bipolar transistors than you would have in a classical silicon transistor. And then we'll conclude. Now, there are not too many great references. You can, this first reference, heterojunction structure fundamentals, this is posted on the web. And also Herbert Kromer, who won Nobel Prize for this, he also has a great paper. But I'd primarily ask you to follow the lecture and not go around looking for too much new material, because that is probably not necessary. Now, as you remember, the topic we are discussing is the dilemma of an engineer who is trying to build a great bipolar transistor. Until 1980s, people used to do it by all silicon. Silicon for emitter, base, and collector, all silicon transistors. And you could manipulate the doping, the emitter doping higher than the base doping, the collector doping a little lower. You could manipulate the doping to get great gain. And subsequently, people tried with polysilicon transistors, right? Polysilicon suppresses the base current, and therefore you have good gain. But at the end, as I have mentioned to you in the last class, that at the end, of course, the polysilicon can only limit the current to V sub S, the last term, and on the denominator, which is the sort of the recombination velocity or effective recombination velocity to the polysilicon, which suppresses the gain, but it can only suppress the current, base current, only by a certain factor. And the problem is that as you keep making your base smaller and smaller and smaller, eventually you have that V thermal velocity limiting your transport or gain. So at that point, you really do not have any other options but to look the only and the sole remaining factor, which is this intrinsic carrier concentration, Ni squared in the base and Ni squared in the emitter. This immediately gives you an idea that how to make a better transistor. So, for example, if you could make somehow, if you could make the emitter band gap larger, then you realize that on the denominator, the blue Ni squared, that will have a Nc and Nv, you know, these are effective density of state. That's what quantum mechanics hides and all those things. But the main point is, the main factor is e to the power band gap multiplied by beta, which is kT, 1 over kT. Now, the band gap for beta, band gap for the emitter is E sub g comma E, and correspondingly you will write out the one for the base, right? You will write out one for the base, but you can see that effective density of state, well, more or less, they are about the same, 10 to the power 22 or so, let's say. Now, so the only remaining factor, and the big factor at that, is the difference in the band gap. And you can immediately see if the emitter band gap is larger, then the blue factor will be larger than the red factor in terms of the band gap, and you will have an exponential increase in the gain because of the increase in the band gap. Now, this is an idealized case. We'll see that reaching this limit is not really that easy. So, do you remember that essentially these devices are all vertical? We take a one-dimensional cut, rotate it 90 degrees, and generally plot it out this way. And in the emitter region, I have indicated in red that the band gap of region 1, which is emitter, is larger than band gap of region 2, which is the base. Now, in this particular case, we have the band gap for the base and the collector are the same, you see, Eg2 and Eg2. What does it mean? It means the emitter is of different material, but the base and the collector are made of the same material. However, there is something called a double heterojunction bipolar transistor, where the emitter, base and collector band gaps, all three are different. The problem with the previous version of the single heterojunction bipolar transistor is that for the collector, many times if you keep the band gap small, then when you apply a large bias, then the collector generally breaks through impact ionization. So there is a loss of control of charge. So what people generally do is on the collector side, they again use a larger band gap material such that even when you apply a large bias, it doesn't break so easily. Break meaning through impact ionization. The transistor doesn't lose control that easily. But this again brings in additional fabrication difficulties as well as conceptual problems that we will see. Now, most of the transistor, of course, doesn't look like this, or none of them. The actual transistors would look something like this. You will see it looks like a mesa. You start with a semi-insulating substrate. Semi-insulating substrate means that this is made of semiconductor, but you have so many defects that you intentionally introduce that the Fermi level is pinned in the mid gap. So it's almost like a insulating material. So it's called a semi-insulating material. Why do you need it? Because semi-insulating material have very low conductance. As a result, because these transistors will be used in extreme high frequency. Do you remember in the last class we said that if you have too many junction capacitances, that reduces the FT of the transistor? Do you remember? That the junction capacitances must be suppressed. And by using a semi-insulating substrate to begin with, you reduce the capacitance. So therefore, it will go to a very high frequency. You can see the N plus collector, N plus sub-collector, which is the red, and N collector, and P plus base, and then N. These are essentially you start with a larger device, you sequentially H to define these various regions. Now, there are many applications, of course. First of all, in optical fiber communication, this is when I was in Lucent, I worked on 40 gigabit systems. So many of these very high performance systems are actually made of HBTs. Now, of course, there are A to D converters, and mostly these days, these are military applications for very high frequency equipments. And these days, people are talking about even a terahertz transistors, but all based on HBT. So if you go and take a job at any of the defense contractors, this is what they will have you start working on. So having a terahertz power gain cutoff frequency, FT, remember? Oh no, this is power gain. So power gain, what was the factor? There was one was FT and another was, do you remember? F beta. I don't remember. I just I'm losing it for a second, but I'll come back to that. So on that one, it's a power gain, not the normal gain of the current itself. So there was a second definition, and so that is the second cutoff frequency that one has to define. So you can see how a actual transistor looks like. Let's focus on the left. Looks like one of those Mexican temples, right? You see subsequent mesas defined one top of each other, And you can also see, emitter, base, and a collector. And you can see that the emitter and the collector and base, the contacts are coming in like a flying serpent, right? It's like and the reason is, of course, reducing capacitance is everything, because by removing the material from underneath, you are removing the line capacitance. Because unless you remove the line capacitance at these high frequencies, before the signal comes to your device, most of them will bypass and will return back to the source and will not reach and will not be amplified by this transistor. And you remember, I mentioned it a few times, that Kromer won Nobel Prize for defining the concepts of HBTs. Of course, the original concept is still due to Shockley. Shockley did everything. He was, of course, a genius of the highest order, but the actual potential of how to use it and wide variety of ingenious techniques are all due to Kromer. And the Kromer essentially worked out all the details, and so he is primarily credited with this technology. So after all these interesting stories, getting back to business of equilibrium solution. So the first thing is that we'll have to grow material on top of each other, right? So for example, we might have an aluminum gallium arsenide emitter, and the base could be gallium arsenide. Or we could have indium phosphide as the emitter, indium gallium arsenide could be the base. So these are different materials. Now you cannot simply take a material and put another material on top of it, because as soon as you try to put another material, there will be defects forming unless their lattice constants are about the same. For example, the aluminum gallium arsenide emitter, gallium arsenide base, look at this. You see aluminum gallium arsenide that has a certain band gap, let's say about 2.12, something like that. And then you have gallium arsenide over there, both having on the x-axis a lattice constant which is about something between 5.65 or so. Since they both have the same lattice constant, when you grow aluminum gallium arsenide on top of gallium arsenide, they essentially nicely match up. Their atoms nicely match up, and so there's no strain and no defect generation. So therefore, these you can use for making an HBT. Now, many times you would also like to use, let's say, indium phosphide. Do you see in the middle, indium phosphide is right in the middle with a lattice constant of about maybe 5.9, a little less, and band gap of 1.3 or so, let's say. Now, in that case, if you want to have another material right underneath for the base, the right one would be a combination of, let's say, indium arsenide and gallium arsenide. Do you see the bow-shaped line and the red point sort of sitting in between? So you'll have to take a combination of, indium arsenide and gallium arsenide, mix them, and then have a material whose lattice constant is just about right for indium phosphide. And then on top of it, grow indium phosphide. This is why we studied, remember all the lattices we studied, the lattice constant in the beginning of the semester. This is why we studied this, because without this, many of the technological features would be impossible, right? So lattice and the lattice type and structure is very important to define a particular technology. Now, these days, there are wide variety of combinations for various materials, for transistors, for solid state lighting, and all sorts of things. So this would be an indium phosphide, indium gallium arsenide transistor. So let's solve the Poisson equation by this graphical method, and that's the band diagram. And rules are exactly the same. I cannot remind you too many times that you draw the Fermi level. One side is N, the larger band gap side, let's say, on the emitter is N. So you put the larger band gap side as N, and let's say for this particular case, aluminum gallium arsenide, this is 1.8 eV, let's say. You will put the vacuum level with chi 1. Similarly, you draw on the other side. You can see that this other side is p-type and also has smaller band gap. Remember, this is going to be the base, and the base must have smaller band gap compared to the blue emitter. So I'm putting this red as a smaller band gap, p-type. Chi2, of course, you have a certain work function depending on the material. Whatever material you have, if it's gallium arsenide, you will have certain Chi2 that you will read off from the book. And then you will make this whole thing continuous, copy them down, and that completes your band diagram. That's it. Now, you see I have written a word called type 1. This is a type 1 heterostructure. What it means that the band gap of the small one fits right inside the band gap of the large ones. So therefore, you can see there is a drop coming from emitter to the base, from the n-type to p-type, the electron going down, and similarly coming from the n-type to p-type, the holes also there is a positive delta EV. There is a change in delta EC and delta EV, so the band gap of one is fitting right inside the other one. This is called type 1 heterojunction, because soon we will see cases where the one band gap and the other band gap will stagger such that in one case the delta EC is positive, but the delta EV is actually negative. So those will be other types that you can see. There are possibilities here that homojunction transistors, silicon transistors, of course wouldn't have. Right. So, okay, so you know how to draw a band diagram then, and these would be called abrupt heterojunction transistors, because one material abruptly stops, emitter stops, and then another material begins. The composition of the material doesn't change as a function of position. What is the composition? You can see on the top that 30% of the gallium atoms in gallium arsenide has been replaced by aluminum. So that's what it says, aluminum 0.3, gallium 0.7, and arsenic, that's for the emitter region, and that's 1.8. Now again, the first thing you do with these things is VBI. You calculate VBI, right? I'm doing the same thing over and over again. There should be no mystery. How do you do VBI? No rocket science again. Delta 1 plus chi 1 plus Q VBI is equal to EG, the band gap on the second side, right on the red, plus chi 2, and you have sort of gone over. So you have to take out minus delta 2, you know, this minus delta 2 business. And you know this delta 1 and delta 2. How do you calculate that? You know the doping, and so therefore you can easily calculate the how much the delta 1 and delta 2 are going to be. So it's very easy actually. You put in the values for delta 1 and delta 2, and remember the two sides do not have the same effective density of state, right? Two different materials. So how you wouldn't have this you'd have different effective density of state. You can see NV2 and NC1 and so on and so forth, EG2, and that's taken care of. And chi 1 and chi 2, of course, you read it from your table or from a book from that material. This is tabulated. How do they get chi 1 and chi 2, by the way? These are all this photoelectric experiment, you remember, which allows electrons to be pumped up into the free region so that it can be collected. So from the first part of the course. Okay, so you know QVBI. If you know QVBI, then the rest of the things are easy. Do I remind you one more time that if you have two different material, then you have this kappa 1 and kappa 2, and the electric field is not continuous, right? Electric field is not continuous. What is continuous? Displacement. D, the displacement is continuous. Displacement is continuous only if, by the way, and especially in heterojunction bipolar transistor, if you do not have any interfacial charge. If you have charge between base and the emitter, let's say the defective layer, you have not been able to grow it very well, a defective layer, then D1 minus D2, right, will be equal to the charge that you have in the interface. If you do not have any charge, then these are the relationships. That's what you're assuming. Okay, these we have done so many times, we should be experts now. You again realize that NDXN and NAXP, which is the depletion on the two sides, are inversely related to the doping on the two sides. So we know that. right? So you can always write this. And you see this first relationship is essentially a charge conservation relationship. It really doesn't care about whether you have kappa 1 one side, kappa 2 on the other side. It really doesn't care. But on the second one, it does. So when you have VBI, then in order to have VBI, you have to have the area under those triangles for the electric field, right? For the blue line and the red line. And correspondingly, you have this electric field at 0 minus multiplied by xn, and electric field at 0 plus multiplied by xp divided by 2 is the triangle. And so you can correspondingly calculate, insert the values of the electric field, you can get the expression for VBI. 2 unknowns, 2 equations. Well, you have done it many times. You know how to do it. Xn is only the same expression as before, except you see these 2 relative dielectric constants sitting there. Does it look about right? Had it been the same material, had both sides been silicon, then the 2 kappa should have been the same, right? On the emitter and base, do you see? If the kappa had been the same, on the numerator you would have been kappa squared. On the denominator you would have pulled out a kappa. Get rid of one of the kappas, old result for silicon. That is how it should be. And then correspondingly you can get a value for xp, and therefore now you can correspondingly find the depletion region. One thing you realize, because I have this gain through band gap difference, I'm no longer constrained with having the base doping lower than the emitter doping, because now emitter doping could be lower than the base doping, but so therefore in general the gain could have been less than 1, but because I have this band gap difference, that is giving me so much that I can spend it for inverting the doping sequence, right? And that is the whole point about heterojunction bipolar transistor. I do not have any problem anymore with early effect because my doping, base doping is large. So no problem with that. And correspondingly, my Kark effect is also suppressed because now I can raise the collector doping. So all those problems are gone because I can take advantage of the gain, get a lot of gain by the band gap difference. You see, that is the central point why we do this. Okay, so few more types of heterojunctions, and then we will be done. What is the difference between the picture that I just drew a few minutes ago and this one? It's same aluminum gallium arsenide system, except it looks very different. Why does it look so different? Because it is actually p-type for the emitter and n-type for the base. Do you see that? Do you see that the green is again the flat Fermi level, and on the base side, do you see that it is, or on the n side, in gallium arsenide side, the conduction band is very close to the Fermi level, you see that, and correspondingly, valence band is very close to the Fermi level on the n side. By the way, one comment about the symbol, anytime you see a capital P, that means that's a larger band gap region. Because otherwise, you know, many times, just from the material given, unless you look up in a book, you wouldn't know what the band gap is, right? So that indicates to you that the larger band gap is whatever has this larger capital symbol that has the larger band gap. Now, it's again, you can see the delta EC and delta EV both are positive. Of course, this is the original combination of materials, and therefore it's still, of course, type 1 junctions. Now, let's talk about type 2. Type 2 junctions. This is another lots of places there are various applications. So again, I'm doing an n-type on the emitter, same rules. But this time, you see the band gap does something like this. Now, that's a type 2, because you can see the red one is not fitting inside. It's not fitting inside the blue one, but rather delta EV is negative, they're going the other way. Delta EC is positive, just like the previous type 1 transistor. that's fine. Now, the heterojunction transistors also allows you to do isotype. Isotype meaning N and N. You know, previously in silicon, if you had N and N, that wouldn't be very interesting, right? It's a sort of uniformly doped material. Now, if you had a little bit of doping change, maybe there's a slight variation, not too much. But for heterojunction transistor, even the isotype, meaning both sides N, could be interesting. You can see here, both sides is N-type, and you could also correspondingly have both sides as P-type and correspondingly draw a band diagram. Now, I'm not stepping through the steps to create this band diagram, right? But when you are in your home, you should check to see whether you can draw these band diagrams yourself. Now, one thing you realize on this band diagram, that although both sides are N-type, but in one side you have a depletion region, right? Because charges have been pushed back in one side, so you have a depletion charge. However, on the other side, you have accumulation. On this little notch, you will have electrons. And this, therefore, you cannot use the depletion approximation we used to calculate this xn and xt. Remember, those are supposed to be purely space charge, that the mobile charges have been pushed away, only the donors have been exposed and the acceptors have been exposed. And in that case, we could calculate those charges. Here, however, on one side, yes, charges have been pushed back. And so, therefore, on the larger band gap side, yes, you can have this depletion charge. But look at the other side. In fact, charges have come in because it has gotten closer to the Fermi level, the rate Fermi level. So, therefore, I cannot use my standard depletion approximation, QVBI and all those formulas. Now, how do you calculate it? Well, that will be another course where you will learn how to do this. But for the time being, you can either just understand it, and if you do numerical simulation, you know, through NanoHub, they will do all these things automatically. So, you don't have to worry about it. Now, by the way, one thing people often say, that if you have two metals, this is an exam problem I often give, that if you have two metals, do you have a barrier? And most people say, well, I have one metal, another metal, lots of electrons, no barrier. Not really, because of course, metals similarly have different work functions, and when you bring two metals in, you will have correspondingly a corresponding discontinuity. That's how you make thermoelectric coolers, or because you have many times two metals that comes in, you know, your picnic coolers, sometimes you take to picnic, in order to keep it cool, many of the junctions, thermocouples for example, two metals coming in, you heat one junction, cool another junction by passing current through it. That happens only because when you put two metals in, they do not have the same band lineup. So, when the electron goes over from one metal to another, it can lose energy or it can gain energy through that notch. So, it's a very practical thing that you see and use all the time. Now, there is a type 3 also, and type 3 is really bizarre. Let's look at it. So, this time that you can have a band gap like this strange. So, let's say I have this gallium antimonide and indium arsenide. This two I have. And so, I'm drawing the same band diagram, and you'll have to sort of put it in same continuity of the valence band, vacuum level. You can do that, and when you do, you see that this again is, let's say, p-type on the p-type on the emitter side and n-type on the base side, let's say. Do you see now the band gaps through two sides? The band gaps even are not inside each other at all. It has been completely shifted out. Right. And you can correspondingly see that in this region, very strange things are happening. There's no depletion region per se. On both sides, carriers have accumulated. On one side, what has accumulated on the left side of the junction? a bunch of holes, a huge amount of holes have accumulated. On the right hand side, what has accumulated? Electrons, because look at the Fermi level, the green Fermi level has gotten inside the BAP. That means that this is now has become degenerate. So yes, you always have that balance of charge. You have P charge on one side, the holes, and N charge on the other side, the electrons. You have the balance of charge, you have the junction, but these charges are not space charges. These are mobile charges. And so therefore, this behaves in a very different way than corresponding to a normal junction, or quote unquote normal junctions that we know about. So let me conclude on this part. So we talked about heterojunction transistor, and it offers the solution to the gain problem associated with polysilicon transistor with extremely short base. Because you see, we got stuck, we couldn't get any gain, and the base doping, if I needed the base doping to be lower than the emitter doping, we were in trouble. So therefore, we got out of the trouble by manipulating Ni squared, and that gave me a lot of gain that I could trade off against other thing, and still could have a fantastic gain. Now, equilibrium solution of HBT, of course, this is just like normal BJTs, bipolar junction transistor, but of course, I have many more options, type 1, type 2, type 3, depending on how the bands bend, what materials you have. Now, if you do not follow the rules, right, there's no hope that you will get this band diagrams right, because this is complicated enough that you can never memorize these things. If I give you a combination of material, right, from, let's say I pick something up from one of the papers in the literature, if you don't follow the rules of these things consistently, which takes a few more minutes than just memorizing it, then you will be in trouble. So let's follow the rules. Now, as I said, 3 different types of heterojunctions. The first one is type 1, where the larger band gap material completely nestles the smaller band gap material. The other one is staggered, where the valence band is out of alignment, but the conduction band is still inside, but it could go the other way also. Valence bands could be inside, and the conduction band could go outside. That's all type 2. And type 3, well, they don't even talk to each other. They are essentially completely misaligned. Now, for type 2 and type 3, we wouldn't use the classical depletion approximation in order to get the band liner. Now, we haven't talked at all about current transport, the gain, and all other things. That we will do in the next class.